Redox in a beaker. Now this is still one of the introductory lessons on electrochemistry. In this video I want to introduce you to the microscopic reactions that take place in a beaker, as well as the standard reduction potential table, commonly known as the E0 table, which allows you to predict whether a reaction will occur or not. So let's get started. So let's look at this situation. Here we have a strip of copper sitting in a solution of copper sulfate. In other words, we can describe this as copper in a solution of its own ions. Now, if you were to observe this for some time, would you see anything happen? Well, the answer is no. There would be no observable reaction on the macroscopic scale in our world. However, on the microscopic scale, there is lots going on. If we look at this diagram, this shows that occasionally a copper atom may leave the strip and go into solution as an ion, leaving its 2 electrons behind. Since there are many copper ions in contact with the strip, then almost immediately a copper ion will pick up these 2 electrons, become neutral copper atom, and plate itself out on the strip. So this is going on as an equilibrium shown here. Now let's look at a different situation. Here we have the strip of copper sitting in a solution of silver nitrate. So this is copper in a solution of different ions. When a copper ion comes into solution, there is now a competition between the copper ion and the silver ion for the electrons on the strip. And the question is, which one wins? Now you might suggest that because copper has a stronger charge over silver that it would win, and that would be quite reasonable. However, there is more chemistry between these ions which we can't allow us to make such a basic prediction. In fact, we find by experiment that it's the silver that wins. In other words, it has a stronger tendency to gain electrons than the copper ion. This can actually be measured by a voltage in an indirect way, and it's written like this. The tendency of silver to gain its electron has a value of 0.80 volts. E is the voltage. It stands for electromotive force, means the same as a voltage. And in a minute or so I'm going to be coming back to this E0 table and explain it in some detail. But right now this gives us a sense of the strength of attraction between these two. If we look at the situation for copper going for the 2 electrons, its value is only 0.34, and because it's lower than this one, this is how we know that the silver will win. Now before I go further, I'd like to show you an interesting video. This is a very well-known experiment or demonstration called the silver tree. Here we have in solution we have the silver nitrate. The copper goes in and almost immediately gets a silvery color. This reaction going forward. What is also happening that you can't see is the reverse reaction of copper being oxidized to copper ion. You know that the copper 2 ion produces a blue color in solution, and gradually as the concentration of this increases, then we will see the blue color appear. So although this is a redox reaction, this is also a single displacement reaction where the copper is displacing the silver. So the silver is coming out of solution and copper is going in. So after some time here we see nice silver crystals, and there's the blue color showing the presence of this copper ion. It grows quite a while, and here the demonstrator is showing how it's easy to shake them off. And if you look at the copper, it doesn't look like it's changed. In fact, it is slightly thinner than it was at the beginning because of the amount that went into the solution. There are some terms here that we need to be familiar with before we go on. Now, E0, this electromotive force again, which I'm going to be coming to in a minute, the 0 here refers to standard conditions, and the standard conditions are 25 degrees Celsius for temperature and that any ions that are present, their concentration is 1 molar. Second idea is to understand that the larger the E0 value is, the stronger it is the tendency to attract electrons. Third point, a positive E0 value means the reaction is spontaneous. If you see a negative value in a reaction, it means that that reaction is not going to happen. So, for example, here, if this was a -8, it means that silver would not tend to unite with an electron to form the metal. Fourthly, if you write the equation in the reverse manner, the sign of E0 reverses. That's going to be important when we do problems with this. And fifth, the size, the magnitude of E0 is independent of the amount of reactant. Now, you can easily understand this if you think of your dry cells that you're familiar with. The AA, C, and D cells, they all differ in how much reactant there is, but they're all 1.5 volts because the chemistry is the same, and it's the chemistry that determines the magnitude of the voltage. The fact that there's different amounts of reactant simply determines how long they're going to last. And as you know, the larger cells, D cells, last longer than the AA's, and the AAA's are sometimes infuriatingly short-lived. Let's have a look at the so-called E0 table. It is really a table of standard reduction potentials. You'll notice, first of all, that all these reactions are written as equilibria, so they can go both ways, and that all the substances on the left are gaining electrons on this side as well as on the rest of the table shown here. So that qualifies this as reductions. Now, the positive voltage means that the reaction as written from left to right is spontaneous. But down here, when you get to the negative voltage, it means as written from left to right is not spontaneous. However, the reverse reaction, because it's an equilibrium, the reverse reaction will be spontaneous, and the signs for E here now will be positive. Going back to the top here to look at fluorine, you can see that it has the strongest attraction for electrons. It has the highest E0 value. And so it is a very strong oxidizing agent. So remember that the agent is itself reduced. The strong oxidizing agents, some common ones, are permanganate ion here and chlorine. And let's go down to iodine. Iodine is known as a good disinfectant for wounds. And the way it works is that when it comes into contact with bacteria, it will remove electrons from the bacteria and so kill them. Let's now look at, go down to the value of 0. So at 0 here we have what is called the standard hydrogen electrode. So none of these reactions by themselves can be measured individually. You have to have a reference by which to compare them. And chemists decided at some point that this particular equilibrium between hydrogen ions and hydrogen gas will be selected as the standard, and then all these other half reactions, which can be constructed as half cells, would be hooked up to this particular one, and then the difference in potential can be measured in volts. Now this standard hydrogen electrode will be discussed, the construction and operation of it separately in a separate video. Now the strongest reducing agents are down here at the bottom right of the table. You see they have the strongest negative values here, but if you look going from right to left, then they are positive, and they act as reducing agents because they give off electrons. So remember, potassium, sodium, and to some extent lithium are very reactive in water. So lithium has the highest potential here, even though it's not as active in water. That's because these values are based on the individual atomic properties of these elements in solution, whereas when we watch these things in water, we're looking at a mass or aggregate behavior, and that's a little bit different from the individual behavior. Now once these ions are formed here, they have their stable octet structure, or in the case of lithium only 2 in the outer shell, which is stable, and they don't react further with anything else. So this is an overview of the E0 table, and we'll be making extensive use of it in electrochemistry. Using the E0 table, let's look at a question like this, which will allow us to make use of the table. Which is a stronger oxidizing agent, copper 2+ or silver 1+? I'm using an example that we're already familiar with, so let's go and have a look at the table now. We're looking on this table for copper 2 ion right here being reduced to solid copper, and here's its reduction potential of 0.34. We're now going to compare that with silver ion here, going to silver solid with a reduction potential of 0.80. And so here we have our answer. Since silver has a higher reduction potential, that makes it a stronger oxidizing agent. Now just before we leave this, I want to point out the danger of not paying attention to these ion charges. So here, for example, is copper 1 going to copper, which is not the same as copper 2+ going to copper. And down here, here's another reaction between copper 2+ and copper 1+. So be very careful when you select the half reactions you're supposed to be looking for. So returning now to our question. Here is our answer. Silver ion is got the higher reduction potential as mentioned compared to copper, and so that makes it a stronger oxidizing agent. Now, where do we find the strongest oxidizing agents in the table? So they are in the top left section, and the common strong ones are hydrogen peroxide. You should know some of these: potassium permanganate, chlorine. Potassium dichromate is perhaps not as well known, but these are strong oxidizing agents when they're needed in chemical reactions. The strongest reducing agents are found in the bottom right section, and the reducing agents, remember, are good at losing electrons. In other words, they're good electron donors. They give up electrons, and as we've seen, for example, lithium and potassium, written this way, are very strong reducing agents. If we wish to know whether two particular substances will react with each other without going through calculations, there's a neat trick or shortcut we can use using the E0 table. The rule for that is that any species on the left side of the arrow reacts spontaneously with any species on the right if it is below it. Now, I know the word species conjures up biology, but chemical species is a legitimate term. So how it works is this. Suppose we have two reactants, and one of them is in this position, and the other one is in this position. Then you can see that you can, going from this reactant to this reactant, traces out a clockwise pattern, and that means then that this reactant and this will react spontaneously with each other. So let's look at some questions here to see how to use that table. We'll look at this one, which we're already familiar with. We have to go to the table and look for the relative positions of the silver ion and copper solid. So we look for silver ion. Here it is up here. And now we look for copper solid, and we find it here. And here's another one. Now, which one do we use? Well, notice that this one leads to copper 1+, and that's not a very common species in chemistry, whereas this copper leads to copper 2+, and that's by far the more common one. So this is the reaction we're going to use. So you notice that the copper is to the right and underneath the silver. So now you can see how we can trace out this clockwise pattern, showing that these two will react in a spontaneous manner. So now we can see from the table that the silver 1+ is on the left and above the copper solid, which is on the right and below, and therefore they will react with each other. So here are some more questions that you can stop and try using the table and see how you do, and the answers will follow. Now, to finish off, let me just go over the solutions for B and C. Both of them involve chlorine, one to react with tin 4 plus and the other tin 2 plus. Let's see where they're located in the E0 table. So here we find chlorine way up here. It's a strong oxidizing agent, so we'll hold that first. It goes to chlorine minus. And now the two forms of tin 2 plus and tin 4 plus. Here's tin 4 plus, and here's tin 2 plus. And there's also a tin 2 plus down here. Now, chlorine is on the top left. Here's tin 4 plus underneath, but it's on the left. So therefore, chlorine cannot react with tin 4 plus. But here's tin 2 plus on the right and below chlorine. So that will work because we have this our clockwise pattern. So chlorine and tin 2 plus will react spontaneously. There is another tin 2 plus down here. However, it's on the left and not on the right. So reducing tin 2 plus to the tin metal won't work with chlorine, but tin 2 plus will be oxidized by chlorine to form tin 4 plus. That's the end of this lesson.